All right, everyone. So, so welcome to this second and last talk of the morning. So it's my pleasure to welcome Diogo Oliveira Silva, who was up until the end of March my colleague in Lisbon, right? So we're technically at the same university. He's a good friend of mine. It's good to have him back at Rio after almost perhaps 10 years, right? Mm-hmm. And Diogo is going to be talking about dimension-free Fourier restriction inequality. So Diogo, please.
Yeah, thanks a lot, João, for the introduction. Thanks a lot to the organizers, Mateus, Emmanuel, Felipe. It's really great to be here. So just like Jose, I was trying to find some memories from the last time I came to IMPA. This was 10 years ago. I had a hard time, but then I looked a bit further and I found something. And so this is up in Cristo. There's the Pão de Açúcar. I was clearly having a very good time. I'm also having a very good time this week. So thanks for putting this together. Back to the title. So there's two parts in the title. Dimension-free and Fourier restriction. So this is joint work with Błażej Wróbel from Wrocław in Poland. He likes everything related to dimension-free. I like everything related to Fourier restriction. So at some point, a couple of years ago, someone commented, if you guys ever write a paper together, the title should be dimension-free Fourier restriction inequalities. And that's exactly what we did. So the paper is on arXiv. It has this title. Of course, I know less about the dimension-free aspects of things in general, in harmonic analysis, so I will start there. As far as I understand, the initial motivation came from considering Hardy-Littlewood maximal functions and to make these estimates dimension-free. So this is how the history goes. One way to introduce it is to fix a convex symmetric body, call it G. G sub t will be a dilation of G, and we consider an averaging operator. Okay, so basically you integrate a given locally integrable function f on the ball centered at x with a copy of gt around it. You average it, and that's what you call the MTGF at the point x. You take a sup of the absolute values in t to make it a maximal operator, and you're interested in LP bounds for this object. In principle, these bounds will depend on the exponent p, on the dimension d, and on the convex symmetric body G that you started from. There are some very simple observations, namely if p is infinity, this is an averaging operator, so constant 1 will definitely do the job. Because of various covering lemmas that everybody knows about, if that's the case, then you get a finite CP constant for every p strictly larger than 1. But these covering arguments, Vitali, Bezikovich, whatever, they're not so great from the dimensional point of view, right? You have an exponential dependence in dimension, generally, and so if you're interested in dimension-free bounds, this is not the way to go. Why should you be interested in dimension-free bounds? Well, there's a number of possible motivations. Usually, a dimension-free estimate is an estimate that's intrinsically infinite dimensional. Easier said than done. There's no Lebesgue measure in infinite dimensions, so the arguments don't go through automatically, but there are versions of these arguments that do. For instance, if you think about usual LP bounds for Hardy-Littlewood maximal function, one of the reasons why they're interesting is that they tell you about the possibility of differentiating integrals, right? Lebesgue differentiation follows from some sort of weak type bounds for the maximal function, and you can try to do the same thing in infinite dimensional spaces with Gaussian measures. Okay, results about the differentiation of integrals in infinite dimensional settings, they come from dimension-free bounds for Hardy-Littlewood maximal functions. Okay, so what's actually known? I think this was inaugurated by Stein in the early 80s. He has a very nice paper called Harmonic Analysis in RD as d goes to infinity, and one of the things he checks are dimension-free estimates for this constant CPD of B2. B2 is the ball coming from the L2 norm in RD in the whole range of admissible P. Okay, P2 is fine, but that's not the only convex symmetric body. So more generally, if you just take any G, then there are dimension-free estimates for Cp of G if P is bigger than 3/2. I think the history is that Bourgain first did it for P equals 2, and then he extended to all P greater than 3/2 at the same time as Carberry. Okay? All right, so it's, and what happens between 1 and 3/2 is still open. Of course, there are concrete cases of convex symmetric bodies that may be easier to handle, and one of them is the ball coming from the LQ norm, the BQ, and that's what Detlef Müller considered in 1990. He did it for every finite Q, and then several years later, Bourgain came and proved the final missing estimate for Q equals infinity. And this might give you an impression, so every time we have a bound, it's probably going to be dimension free, right? Wrong. And a striking example of such a result came from the work of Aldaf in 2011, where he showed that no dimension-free bound holds for this quantity here, which I haven't really defined, but you can imagine what I mean here is for the weak type 1-1 bound. Okay, so with a cube, with a ball in the L infinity norm be infinity, so no dimension-free bound holds there, and that's why this is an interesting problem. Okay, sometimes it holds, sometimes it doesn't, and when it does, there are applications. All right, another application that I like that comes from this line of reasoning comes from number theory. So the Waring problem is very classical. It was formulated in 1770, and it goes more or less around the following lines. So for every k, there exists a d, such that every integer n can be written as the sum of d kth powers of integers. The problem was solved when k equals 4, more or less at the same time when it was formulated by Lagrange. It was solved in general for every k by Hilbert in 1909, but both of these solutions were very qualitative. So this is a question about existence, and the proofs confirmed, yes, that there exists such a d. Of course, you may want to try to make that more quantitative, and that's one of the reasons that motivated the birth of the circle method of Hardy, Littlewood, and Ramanujan. In the 1920s, they developed analytic tools to try to get a quantitative control over this quantity, Rkn, which measures the number of ways in which this thing that we know is possible can be done. Okay, and there's a famous formula that involves a main term. The main term contains an arithmetic object, that's a so-called singular series, then some powers of the gamma function, which depend on k and d, there's an exponent in n, and there's a remainder term with a smaller exponent in n. And of course, the remainder term comes with an upfront constant. That constant depends on k and d, and so it's definitely not dimension-free. Very recently, just a couple of years ago, these three authors, this is Jaroslav, Mirek, Suomian, and Vrubel, established a dimension-free version of Waring's problem. Okay, so dimension-free because, well, the statement is very similar. There's this formula for the number of solutions. Now the error term is multiplicative, and it's dimension-free. How did they do this? Well, at least in some cases, they related this problem to dimension-free estimates for variants of the objects we have in the previous slide. Okay, not the Hardy-Littlewood maximal function, but these discrete spherical maximal functions. And there's a number of connections, and I personally find it quite interesting that dimension-free maximal estimates have applications, direct applications to analytic number theory. Okay. So this is not what the talk is about. I care about the Fourier transform. This is the Fourier transform. Simple formula, hides many mysteries. This is a cartoon of what the Fourier transform does. So you have a signal in red. You decompose it as a sum of waves. Each wave has a frequency. You measure the amplitude of the wave, and that's a proxy for what the Fourier transform does, or the Fourier series. This operator has some very basic properties. For instance, if you start with L1, the Fourier transform of an L1 function is continuous. There's a contraction from L1 to L infinity. That's just a triangle inequality. You can work a bit harder and check that it's a unitary operator on L2. That's the reason why I normalized the Fourier transform to have the 2 pi in the exponent. And you can interpolate these two statements to get contraction from LP to LP prime as long as P is between 1 and 2. Okay, so this last statement is also known as the Hausdorff-Young inequality, even though this is not the way Hausdorff and Young proved it, because at the time no interpolation was available. Okay, so if you check their paper, it's actually a very clever application of successive holders and Cauchy-Schwarzes for several pages. But with interpolation, of course, you get constant 1 and you don't have to work harder. You do have to work harder if you want to make it sharper. That's what Babenko first and Beckner later did to make it sharper. So there's a constant, BP raised to power D. This constant turns out to be strictly less than 1 if P is between 1 and 2. That's why this is a better inequality than the one from the previous slide. And it's sharp in the sense that the Gaussians, at least this function here, a normalized Gaussian, will realize equality in that inequality. Okay, so this result is due to Babenko whenever P prime is an even integer and Beckner in general. And this is quite old. All right, work didn't stop there. 15 years later, Lieb checked that all maximizers are Gaussians. Gaussians are, so the set of maximizers coincides with the set of Gaussians. And Christ in 2014 came up with a stable version of this inequality. So this goes one step further. Once you know the sharp constant and the complete characterization of maximizers, you can ask, how is this inequality stable? What happens if I start with a function that's close to being a Gaussian? Well, if you're close to being a Gaussian, then this LP distance here, this script G is just a set of Gaussians. This term is small, and so you're yourself close to attaining the best constant. Okay, so if you're close to being an extremizer, you're close to attaining the constant that the extremizer attains. All right, so I show this slide because if you want a dimension-free analysis of Hausdorff-Young, it's very easy. I already said that BP is strictly less than 1 if P is between 1 and 2. In D dimensions, you just raise that to power D, and so you go to 0. Not only do you have dimension-free estimates, but you go to 0 as D goes to infinity. Okay? And this may sound a bit surprising if I'm talking about dimension-free estimates, but Hausdorff-Young is a proxy, a toy model for several of the restriction inequalities that we will find, and so this is just to give you a flavor of what might happen. Okay? So on to restriction. Hausdorff-Young is a perfectly reasonable starting place for restriction. It tells us that f hat is defined almost everywhere in RD if f is in LP and P is between 1 and 2. Okay? If f is in LP, P between 1 and 2, f hat is in LP prime, and then LP prime function is defined almost everywhere. This does not mean that we can restrict it to a manifold. Stein's observation came quite a bit later in the 1960s, and he said, yes, actually, as a matter of fact, f hat can be restricted to some manifolds as long as they are curved. Okay? If there's some degree of curvature, then this restriction is possible. Quantitatively, this means that there's an inequality. There's an LP to LQ restriction inequality. And this is restriction because you're restricting it to the curved submanifold, in this case, the sphere. The unit sphere is a good example of a curved submanifold. It comes equipped with a surface measure. And now we're interested in the validity of these estimates from LP to LQ. There's a constant. I denote it with some fancy boldface R to denote the best constant. And the question is, when is this finite to begin with, right? We're just trying to understand the problem. So what conditions on P, Q, and D guarantee that this constant is finite? That's the content of the restriction conjecture. It's a famous open problem in harmonic analysis. First, I guess, written proof I've seen of this conjecture is in a paper by Stein in 1967. And the conjecture, there's two necessary conditions that Stein conjectures are also sufficient. Okay, these conditions are a bit hard to write down, impossible to memorize. The only thing you can hope to do is to draw them on a Riss diagram, which I will do it so that it stays with us for the rest of the talk. Okay, so there's the 1 over P here, the 1 over q. Both vary between 0 and 1. The main diagonal plays a role. And there's this special point, I'll call it the restriction conjecture endpoint, which lives here at the diagonal. And there's that point 2d over d plus 1. So d plus 1 over 2d, d plus 1 over 2d. We've already discussed that the L1, L infinity estimate is kind of for free, right? Because you can always, the function is continuous, you can always restrict. And what these two conditions together say is that the restriction operator is bounded if and only if 1 over q, 1 over p, 1 over q lives in this region here. Okay, that's the conjecture. I'll tell you a bit about the state of the conjecture and all that, but this is the picture to keep in mind. Okay. All right, so as I said, this is for the unit sphere. Of course, the unit sphere is not the only curved submanifold. You can consider many other possibilities. I also put a frame around the sphere because for the purposes of today's talk, the sphere is the most important example. But the restriction conjecture is related to many other problems.
Diogo?
Question?
Can you explain again, please, what is this region that you have outlined?
Yeah. So a point. This is a Riesz diagram for the restriction operator. A point here is of the form 1 over p, 1 over q, and it belongs to the shaded region if and only if that constant R SD minus 1 PQ is finite. So each dimension has a different Riesz diagram. Okay? Good. It's called a Riesz diagram, I guess, because these regions always end up to being convex regions because of Riesz interpolation. Riesz-Torin interpolation, if you want. Say that again? 0 and the 1, like here? Is that what you want? Any further wishes? Or questions? No? Good? Okay. All right, so as I was saying, the restriction problem is interesting in itself. I mean, it explores fine properties of the Fourier transform. But it also has many connections. Has connections with other central problems in harmonic analysis, like Bochner-Ries about convergence of integrals. Kakeya has been on the news recently. PDE. So, for instance, these three surfaces, the paraboloid, the saddle surface, and the cone, if you try to do restriction there, that's the same as doing Strickert's estimates for the solutions of the associated PDEs, which are respectively Schrödinger, hyperbolic Schrödinger, and cone. Okay, so you understand those PDEs if you understand restriction to these surfaces. There's other links via decoupling and local smoothing. Fractal geometry, number theory, additive combinatorics, even theoretical computer science. I think if you ask, I can provide at least one reference for each of these that relate to restriction. Okay? So it's interesting. This is more or less the same Riesz diagram that I have here. There's an extra point that I will comment on about, this Stein-Thomas point. And I will just make three very classical observations about this Riesz diagram. The first one goes back to the 50s. So even before Stein realized that there was a restriction phenomenon, Lorenz Schwarz, the same guy who invented distribution theory, or at least explored it, he didn't phrase things in this way, but in some sense he solved the restriction problem for radial functions. Okay? So Schwarz's observation is that the restriction constant restricted to radial functions, so I need a new notation for that, and that's what I mean by RPQ rad. Okay? That's the same inequality. It's just that you're only looking at radial functions. So you take a radial function in RD, take its Fourier transform, try to restrict to the sphere, see when this operator is bounded. Well, he proved that that's finite, so the operator is bounded if and only if P satisfies this condition, which in terms of the Riesz diagram, which is almost the same as the one on the board, means that you have to be in this rectangle here, right? Maybe I will. Sorry, couldn't point very well. But this is the point, 2d over d plus 1, right? So there's this rectangle here. If you're here, you're bounded from the perspective of radial functions. Outside, you're not. So how could Laurent Schwartz come up with this result if restriction was not a thing? Well, what he proved, what he needed, was that the Fourier transform of a radial function, which also happens to be in LP for that range of P, is continuous outside the origin. Okay? That's a statement which doesn't require the word restriction to be even known. And that immediately implies what you want, because restricting to the sphere is possible if you're continuous outside the origin. Okay? And that's easy. I mean, once you know what you're looking for, it's not a hard result to prove. Okay, so that was the 50s. Then 60s came and Stein formulated the restriction conjecture, and the restriction conjecture was solved in the plane in R2, so for the unit circle in R2, by a sequence of distinguished authors, first Pfefferman, then Carlson-Schorlin, then an alternative proof by Zygmunt. So they all had different approaches, and they got slightly different results if you care about endpoints, but the upshot is that the restriction conjecture has been solved for over half a century. Okay? The Carlson-Schorlin approach in some sense is the most robust. It involves, so you have your curve, you change variables in the integral that defines the restriction operator, so that becomes the Fourier transform of something, at which point you can use the Hausdorff-Young inequality that we saw in the first slide. You rearrange things, so you change variables back, and you get a fractional integral that can be treated with Hardy-Littlewood-Sobolev. Okay, so a combination of two very classical inequalities, Hausdorff-Young and Hardy-Littlewood-Sobolev, yields an almost complete proof of the restriction conjecture in the plane. All right, and then the endpoint Stein-Thomas. This was, well, first realized by Stein that there should be such an L2-based inequality. So this is a special case when Q is 2. Okay, oops. When Q is 2, that means that you're on this line here. And there's an endpoint here, which is so important that I gave it a name. I called it P bullet. And first Stein realized the possibility of such an inequality. Then Thomas proved it all the way up to, but not including the endpoint. And Stein came back and used his, Stein's Stein's interpolation theorem for analytic families to get the endpoint. Okay, so it's a nice story that starts with Stein, goes to Thomas, comes back to Stein. All right. Why should any of this work? So far, I guess I've convinced you that there's an L1 to L infinity restriction estimate, but nothing else. So why should any non-trivial restriction inequality hold, and what's the connection between curvature and this restriction? Maybe it's easier to consider the adjoint of the restriction operator, that's the extension operator, which takes a function f supported on the sphere and associates with it f sigma hat. Okay, f sigma is a measure, you take its Fourier transform, it's given by this integral. And you immediately see that there's a sort of a mismatch, right, between the curved sphere, the sphere is curved, but these plane waves, they're flat. And curve doesn't interact very well with flat, and that's what originates some decay. If you want to be a bit more formal, you can also try to use what in harmonic analysis is called the TT star method, so compose restriction and extension. That's given by convolution with sigma hat. Sigma hat is a radial object that decays at infinity. Okay? It's radial because the sphere is spherically symmetric. So it's enough to see what happens around a ray emanating from the origin. Parameterize that by lambda. You see that that's given by this integral here. This is an oscillatory integral that has a non-degenerate critical point at the north and south poles of the sphere. So stationary phase applies, and the stationary phase estimate predicts this decay here, which is nice, but quite abstract. For the concrete case of the sphere, you can often do more explicit computations. For instance, on the 2 sphere in R3, sigma hat is just given by a sinc function. Okay? Sinc of modulus of xi. So that decay is like 1 over xi, which is precisely what stationary phase predicts when d is 3. Okay? All right. What about dimension-free estimates for these objects? Okay, that's the point of today's talk. So what you see here So I'm glad someone asked about the Riesz diagram, because what we see here is in some sense the limiting Riesz diagram. Okay, when d tends to infinity, both the restriction conjecture endpoint and this Stein-Thomas, which I didn't draw here, but it leaves at q equals 1/2. Okay, so it's this intersection point here. This was the restriction conjecture. This is Stein-Thomas. Both of these guys, as d tends to infinity, they both converge to the center of that square, right? 1/2, 1/2. And so to understand what happens to the restriction operator as d tends to infinity, it's useful to consider this limiting Riesz diagram. The center, again, is the point 1/2, 1/2, and we divide it into three regions, regions A, B, and C. And we make three comments about each, well, one comment about each of the regions. First of all, in region A, the green region up here, what happens? Well, if the dimension is big enough for every PQ in region A, by this, of course, I mean 1 over P, 1 over Q in region A, the restriction operator is bounded. Okay? I mean, take any point in A. Of course, if you're very close to 1/2, 1/2, you might need to travel a long time in dimension until you get some restriction conjecture endpoint, which I cannot use because the restriction conjecture is open, but Stein-Thomas is not. And so Stein-Thomas will, in some sense, live to the left and below that point. Okay? So by interpolation, you definitely get boundedness of that operator. So things look promising, at least for general functions, if we care about dimension-free estimates. Region B is different. It's the red region below. Remember that we have these two constants, the constant for general functions and the constant for radial functions, and constant for radial functions here. And of course, for general functions, I cannot say much. For in all dimensions, the restriction operator will just be unbounded, and that's it. But for radial functions, because of Schwarz's observation, you're within the region of boundedness of the restriction operator when restricted to radial functions. And so, again, for sufficiently large dimension, you have an inequality here. Region C is terrible. Everything is unbounded. Okay? So the upshot is, if we care about dimension-free estimates for the restriction operator, we should restrict attention to regions A and B and see what happens there. Maybe in region A we can say something about general functions. In region B, at most we'll be able to say something about radial functions. There's this yellow line, this anti-diagonal, which belongs to region B. Sorry, I should have said that, but it will have a special behavior, and you'll see it in the next slide. Okay? So that's our first theorem. It basically tells us what happens in regions A and B. C, remember, is not interesting from this point of view because nothing happens there.
So C includes the black line.
Say that again?
C also has the black border, right?
Exactly. C is a closed subset of the unit square. Right. So in A, if 1 over P, 1 over Q is in A, then dimension-free restriction holds in all sufficiently large dimensions. As D goes to infinity, the restriction constant goes to 0. Okay? This is similar to what we had seen for Sharp-Hausdorff-Young as D goes to infinity. In region B, again, here in region B, we can only consider the problem for radial functions, at which point we might be interested to take the limit as D goes to infinity, and there are two possibilities depending on whether you live on the segment, on the yellow segment, or whether you're well inside region B. Okay? In one case, we have dimension-free estimates, and actually the limit is 0. That's if you are in the yellow segment. Otherwise, we don't have dimension-free estimates. That constant, as D goes to infinity, tends to infinity. Okay, so that's one thing. There's a second theorem that's of a different but related nature, which is now not about taking D going to infinity, but about fixing D and checking whether certain estimates, whose even the Lebesgue exponents of those estimates depend on the dimension, and we would like to make them dimension-free. In general, we cannot. We can only prove them with a square root of D dependence, That's, by the way, for the endpoints time Thomas. Okay, so you fix the dimension D. Remember, P bullet was this endpoints time Thomas exponent, which I denoted in the board with ST. And what we proved is a dimensional dependence that's not worse than square root of D. And if you restrict the problem to radial functions, there's no dimensional dependence. There's absolute constants A and B, and the operator norm restricted to radial functions lives somewhere there. And I think this theorem requires a bit more motivation. Why do we think this is interesting? Why did we work hard to prove it? The motivation comes from, do you have a question?
What's the normalization of the sphere information? What's the area of the sphere? Is it 1 or?
No, it's not 1. It tends to 0 as D goes to infinity.
If you normalize it somehow, you know how this behaves. If you put the probability measure instead of the.
Yeah, it's so we were careful in choosing, first of all, the normalization of the Fourier transform. Secondly, the volume of the unit ball to extract the significant results. Of course, things can go weird if one of these two things fail, but we were careful in both respects. Thanks. Okay, so what's one interest of this second theorem? Well, there's this famous conjecture in sharp aspects of restriction theory that the endpoints time Thomas inequality should be maximized by constant functions in all dimensions. Okay, I didn't write constant functions. I wrote characters because there are some symmetries in this inequality. So if you take a function f on the sphere and if you modulate it, of course the right hand side of the inequality is not going to change, and the left hand side has a Fourier transform. So modulation becomes translation, and the LP norm of a translation also doesn't change, right? So accounting for this modulation symmetry, constants become characters, and the conjecture is that actually a full classification of maximizers for endpoints time Thomas on the sphere should consist of precisely characters. In particular, constants should maximize endpoints time Thomas. With our language, that's one possible way of saying it. So here I'm reformulating it in the extension language. I'm saying that L2 to LP dot prime attains equality when I plug in the constant function on the sphere. And of course, I'm also using the fact that the operator norm from LP to LQ is the same as the operator norm of the adjoint from LQ prime to LP prime, right? Okay, so status of this conjecture, not very satisfying at all. So D equals 3 is a somewhat celebrated result of Foskey from 10 years ago. Beautiful proof with another magic identity of different kind from what Dima was telling us about. But there's some magic there that has been studied intensively. D equals 2 is something that should have been solved by now. In some sense, these two cases correspond. They're special because P dot prime, you can check the numerology, happens to be an even integer precisely in these low dimensions. Then it's not, and so these methods don't apply, and several people have worked on it. So this conjecture has been checked for, this is the unit circle in R2, right? So for instance, with Christoph Thiele and Pavel Zorin-Kranich, we check that conjecture for functions on the circle, which only have a certain initial stretch of non-vanishing Fourier modes, okay? If the first 30 Fourier modes are the only ones which are allowed to be non-zero, then this is a theorem. This was extended with more computational power to maybe 100 or 120. Valentina Cicconi and Philippe here, they worked in a different direction. They have a nice result saying what happens if these permissible Fourier modes, there might be infinitely many of those, but they have to have some arithmetic structure, like if they accumulate on powers of 6 or something like that. Then recently, Lars Becker, also in Bonn, I guess Bonn has been a good source of ideas for this problem. So he worked on the physical side of things, and he checked this conjecture for functions which live on antipodal neighborhoods. So you take the North Pole, the South Pole, you define a concrete, effective neighborhood for these antipodal points, and if the function lives there, then the conjecture also is satisfied for these functions. This is relevant because this antipodal concentration is one of the mechanisms that could prevent constant functions from winning the whole game. Well, they don't. And in parentheses, I just have further evidence. So the constants are known to be local maximizers for the circle problem. This is something that Emmanuel and I were thinking about here. 10 years ago, I was not just going to Cristo and Pão de Açúcar, I was also working in his office. And so this is Carneiro, Foski, myself, and Tila. We proved that constants are local maximizers. And this was extended to an initial stretch of dimensions, I think up to dimension 60 by Philippe and Giuseppe. Okay? So lots of activity in this problem, but fundamental questions remain open. And what's the relation between these two things? Well, if the conjecture is true, then by the second part of theorem 2, endpoint Stein-Thomas should be dimension-free. If you just follow the original reasoning of Thomas and Stein, you get a terrible dependence with dimension. I think it's exponential bounds. And so this result reduces from this exponential dependence in dimension to a square root of d, which is still not dimension-free, but it's progress. Okay? So if there's one open problem that I would like to pose, I'm not done yet, but if there's one open problem that I'd like to pose as a result of this talk is please try to get endpoint Stein-Thomas dimension-free. Okay? We've reduced from exponential to square root of d. Please do the rest. Okay, so ideas that go into the proofs. Both theorems 1 and 2, they say something about, yeah.
Can you go back to the prison? Do you expect to be dimension-free? Have you done numerics to see if it's really constant?
I mean, all the numerics I've done are for the conjecture, right? Yeah. And if the conjecture is true, then, which I believe, right? So that's in support of dimension-free estimates.
So it should be dimension-free.
It should be dimension-free, right? If it's not dimension-free, then automatically you get a big D starting at which constants are not maximizers, and you'll have disproved the Stein's conjecture in large dimensions.
Follow-up question, but if you just do this computation, if you compute the LP P prime norm of the sigma head and
here,
by the LP norm of the constant.
Right.
So you say that this is bounded?
Yeah, that's the second part of theorem 2, right? That's exactly the computation that we're doing to ensure the existence of A and big A and small a with upper and lower bounds. And that's why it's important, as Mateus was pointing out, to normalize the surface measure and the Fourier transform.
It doesn't go to zero, right? So
Does not go to zero, stays bounded from below and above. Exactly. Cool? Any more questions? No? Okay, so just one slide about the proofs. So both theorems 1 and 2 have, they say something about general functions and they say something about radial functions. About general functions, so as I said, don't try to mimic Thomas' original proof of Stein-Thomas. You will get an exponential in D bound. Instead, I mean, Thomas' proof is old. There has been many alternatives proposed. There's an especially nice one from PDE, which I think goes back to Janeiro and Velo when they're trying to get Stricker's estimates for more general settings. And they propose that instead of this Thomas approach, you do something that's more closely related to the Carlson-Schollin argument I told you about to settle the restriction conjecture in the plane. So you do a sort of an implicit Hausdorff-Young, followed by a fractional integration in the direction transverse to the hypersurface. We do that together with an application of Lieb's sharp Hausdorff-Young, Hardy-Littlewood-Sobolev at the end. Littlewood is misspelled. Sorry about that. Okay. Once you have that, that's the first part of theorem 2. We get the first part of theorem 1 via interpolation. You just mess a bit around with the limiting risk diagram as d goes to infinity. In terms of radial functions, we need asymptotics for Bessel integrals, and we need them to be uniform and two-sided, from below and above. This is the first time that I say the word Bessel function. Why do they enter the picture? They enter the picture because that formula I showed you for sigma hat on S2 is just one very particular instance of a more general phenomenon that these Fourier transforms, they can be computed in all dimensions, but in general they are special functions. Okay, they are not just sines and cosines. And this is an explicit formula. Here nu is a parameter that depends on D. So in what I'm going to tell you next, every time you see a nu, that's potential danger, right? Because it depends on D, and what we're trying to get is dimension-free estimates. Okay, so we need some two-sided uniform asymptotics for Bessel integrals. Here's one example. This is a classical result that many people in the audience have seen. Goes back to 2000 from Stempak. These are the kind of weighted Bessel integrals that we have to control, and Stempak, at least in the limit where the Bessel index tends to infinity, has pretty satisfactory asymptotics. You see that it sounds a bit complicated. For some reason, it matters whether the exponent p is less than 4, equal to 4, or greater than 4. Alpha, that's the power of r, is a function of p. That's just to ensure integrability at infinity, because these guys decay, and you have to somehow make sure that the thing you're trying to estimate is a convergent integral. And this is something that we've used years ago with Mateus and Emmanuel to put Vega's inequality in sharp form. So you might or might not have heard about this inequality. If you haven't, it's not hard to relate to the things we've been talking about. So there's the extension operator on the sphere, and instead of trying to bound it directly on LQ, we do a radial angle, or Vega did a radial angular decomposition, where the angular variable is measured on L2, and the radial variable is measured on LQ. So this is a weaker inequality than a restriction type estimate. It has the advantage that it holds in a wider range. So Q bigger than the restriction conjecture endpoint is a necessary and sufficient condition for this inequality to hold. And we put many instances of this inequality in sharp form. Okay, in all dimensions, every even integer, we got neighborhoods of even integers and so forth. Okay, and I remember Stempak playing a decent role in that. That was one of the tools that we needed. For us here with dimension-free goals, this is not enough. So Stempak is a problem because the implicit constant in this tilde may depend on p. That's okay, but it may also depend on alpha, and that's not okay. Because alpha, you see, is upper bounded by 1/2 minus 1 over p for the integrability at infinity to be ensured. But there has to be a lower bound on alpha to ensure the integrability at 0. You don't see it here because that lower bound depends on nu, and we're taking nu to go to infinity. Okay? But in general, for our dimension-free goals, constants that depend on alpha are very dangerous. And so we needed a replacement. And here it is. Okay? It's a bit messier, but what's happening here is, first of all, alpha is now bounded from above and below. The bound from below depends on nu, and remember that nu is this dimensional parameter. When d goes to infinity, nu behaves like d halves, also goes to infinity. And what we have are upper and lower bounds. When you see tildes here, they're just absolute constants. Okay, think like 100 or 1,000. They don't depend on anything. And this is the kind of thing we needed. I guess I don't have much time, so I'm definitely not going to tell you how to prove this. I'm going to tell you to spend 5 minutes just telling you about some fun and surprising things that I found related to integrals of Bessel functions. Okay? Here's one of them. It comes from 3 blue, 1 brown. More than 4 million people have seen it, so with high probability, some of you have seen it as well. It starts with this integral that everybody knows how to solve, the sinc function. You integrate it on the real line, you get pi. You can do it in many different ways. Complex analysis, some Feynman trick, whatever. You can complicate this a bit more. You can multiply sinc t by sinc t over 3. It's a bit more complicated, but some fiddling around gives you the same result. Same with 5, and you go on until you get to 13. If you try to do it in Mathematica, mine at least, it starts to stutter precisely here. So better to check numerically what this is. I guess Emmanuel's laptop also has an issue. Then going from sinc of t over 13 to sinc of t over 15, it really takes some time, so you do it numerically, digit by digit. Every digit is a bit painful, but everything goes okay until it doesn't. And I mean, at this point, you start to get worried. What's going on? Is there a bug in Mathematica? Can you really compute this? You can. And this is the solution. Okay? So this is an exact computation. So this integral is not pi. It's pi minus a tiny fraction of pi. It makes it differ from pi in the 10th decimal place. Okay? And so this is surprising, and it also shows up in a related problem on uniform random walks. So a uniform random walk in R2, what's happening? So you start at the origin, and at every time unit, you're allowed a unit step in a direction that's chosen uniformly at random from all possible choices in your unit circle. And you can do it n times, and that's when you have an n-step uniform random walk in R2. This is a probability distribution. It's radial. I'm going to show you some pictures, but I want to highlight the fact that this is related to the n-fold convolution of arc length measure on the circle. They are not a constant multiple of each other. They just differ by this radial factor r, which in dimension d would be an rd minus 1, right? d is 2, so it's r. Okay, here are the pictures. This is P3 to P8. All of them are supported on the n ball, right? P3 is supported on the ball of radius 3. It's a radial function, so you just look at a section. And in some sense, each of these objects is fascinating on its own. For instance, P3 has a global hypergeometric representation. If you try to write down the integral, I mean, it's a complicated integral. You cannot explicitly solve it without using some special functions. And this one happens to be hypergeometric. P4 has some modular properties. So it satisfies this identity here. Here, eta is the Dedekind eta function from modular function theory. That's one thing you can prove about P4. P5, you look at the graph, and it seems like, at least in the initial unit segment, that it's a straight line. It's not. And it differs. So the measure of how far it is from being a straight line is related to the integral from the previous slide, where only a difference at the 10th decimal place is seen. P6 is the kind of thing that you have to understand in order to get a closed form expression for the optimal constant for the L2, L6 inequality on the circle, if the conjecture is true, and so forth. I don't know anything special about P7 and P8, but I'm sure there is. Of course, in the limit, things get regular. This is just the central limit theorem in action, right? As n, the number of steps, goes to infinity, you expect to approximate a Gaussian distribution with some weights. Okay, so these things show up when you're trying to understand these constants and characters maximizing endpoints Stein-Thomas. Of course, for us, it's much simpler, so I'll just finish with one last slide. This is a Bessel function, I think J10 or something. There are three regimes that people who've spent some time with Bessel functions know well. There's an exponentially small regime close to the origin. There's a big bump that is sometimes called a transition region, and then asymptotics kick in, and you have the asymptotic regime. And so one very classical way of doing it is just an asymptotic expansion, and you try to measure the distance or the difference between the Bessel function and the first order term in the asymptotic expansion. The first order term, it oscillates like a cosine, and it decays like 1 over square root. So you expect the error term to be like 1 over square root raised to the cube, r to the minus 3/2. And that's true, but you pay a price, and you pay a dimensional price, which is this nu squared here, right? Remember that nu is related to dimension, so as dimension goes to infinity, that's also out of control. There are alternatives, so this is one thing that we found and used, which is an asymptotic by Krasikov, also with a main term and a remainder. The main term is more complicated because it uses complicated functions, but the error term is uniform in U. Okay, so that's one of the ingredients that we needed in order to get from Stempak to a uniform two-sided Stempak. All right, so this is pretty much it. I wanted to highlight that dimension-free endpoint Stein-Thomas is an enticing problem. If you have any ideas, suggestions, if you'd like to talk, I'd love to talk to you as well. Thanks a lot, and I hope to be back for Fab 2.